Okay, last bit we have here is when K2SO slaps this trooper. I wonder how hard is it? First, let's look at it.
Are you with us? No.
Pretty hard, right?
Pretty hard,
Okay.
yeah.
So let's walk through the calculation. Let's figure out. So here's the first slide here. Can we zoom on top right? Yeah. 0.00 seconds. I think this is just when K2. I think this is just when his arm touches. Can we zoom in there?
Yeah, so you're saying this is when the arm touches. Yeah, okay.
In contact, right? Okay. And then I moved one single frame forward, which is 0.04 seconds. And I think this is still in contact. Can we zoom in? Maybe hard to tell. Still in contact, maybe. Kind of hard to tell. I went one more frame. So that's 0.08 seconds. And here we can see his arm extending off. So there I'm happy that they're no longer in contact.
Yeah.
Which means all the acceleration, all of the actual force application happened in that 0.04 seconds.
So from the K2SO is in contact with the trooper between this time and that time.
Yeah, but once there's no connection, no physical connection to him, you can't be pushing him, you can't be accelerating him. So that means all the acceleration is already done.
Right.
If we can figure out what the acceleration is, we can multiply it by his mass and figure out what the force was.
Okay.
Okay. So in order to figure this out, I need to know how fast, how did he move? Where was the displacement of his body?
Okay.
So if we can zoom in real tight there, I drew this arrow, and this arrow will make more sense with the next slide. But the key point here is that the base of the arrow, the start of the arrow, is in the center of this guy's body, center of mass.
Okay. Roughly the center mass is like right here, belly button.
Yeah. Belly button. And mostly what I'm concerned about is the left-right center of mass. Okay. Then we go to the next slide, the single frame over, 0.04 seconds. And now the tip of the arrow is pointing at his center of mass.
Okay.
And so like his body's a little curvy, but I think that's right. Zoom out a little bit. That in the middle?
Okay, yeah.
Yeah, pretty good, right?
There. Yeah.
Okay, so that's the same arrow. So that means that the base of the arrow, which was just center of mass before, now points to the tip of the arrow, which is center of mass now. So we can figure out the distance traveled in that 0.04 seconds. It's that
you're
much.
saying in this picture, his is the center of mass right as he's getting hit initially.
Yep.
And then this is his center of mass as K2SO leaves contact.
Right.
So this is the displacement
distance
during contact.
You got it. That's the distance over which he was accelerated. Okay, but now how long is that arrow? The length of that arrow, let's look at the picture on the right. No.
Picture.
Yep. So he's standing still. He's, regular human-sized trooper. And so I measured myself. I said from the middle of my body to the side of my body, I got 17.5 centimeters. But if we look in the arrow a little bit tighter, it's a little bit past his body.
Yep.
Right. So I said, I don't know, 20 centimeters.
Okay.
Kind of, so it's a little bit wider than a normal human. Okay. 20 centimeters. Okay. So let's look at the free body diagram and then we'll do equations.
Okay.
Free body diagram. This is when he's the trooper standing still. You get the gravity pulling down. You get so that's Fg pointing down. You get the normal force from the ground supporting him. That way he's not accelerating up and down. And then you get this huge F backhand, this slap.
Yep.
And it's largely to the left. It's a little bit up because we do see him get picked up off the ground.
Right.
Okay. Free body diagram complete. Let's get some equations. So we will use Newton's second law, F is equal to ma. And so the mass of the trooper is, I guess, 80 kilograms. That's kind of a reasonable human weight.
Yeah.
But that
so
acceleration...
if I read this correctly, this is F equals ma. That's Newton's law. Yep. And then you're saying you plug in 80 kilograms for m, and then a is unknown right now.
We'll figure it out in a bit.
Okay.
So what the information that I do have is the position at one time, which he's standing straight up, and then a position at a second time when he's getting flung, he's all S-shaped body. And so I can say the position as a function of time is equal to the initial position. In this case, we'll just say where he's standing was 0.
Yep.
Plus the initial velocity times however long this time interval is. And again, he's standing still. So that initial velocity is 0 meters per second, 0 again. And plus 1/2 the acceleration times the time over which he's accelerated squared.
Yep.
Okay, so the quantity that I want out of this is the acceleration. So I solve for A, multiply that 2 across, take the time squared underneath, and that's going to be our expression there. A is equal to 2 times x of t over t squared.
Okay. So this is assuming this is 0, solve for this A, you get this expression.
That's what I said, but much more concise. Very nice. Okay. Okay, so we have an expression for A, and let's jam all the letters in, then we'll jam all the numbers in. So force is equal to mass times acceleration. Acceleration, we had that one line right above it, 2 x of t over t squared. And then we have 2, and then that x of t, that final position, what we measured was about 20 centimeters, so 0.2 meters. And then we looked from the freeze frames, from the stills, we had 0.04 seconds quantity squared. So this came out to be a very nice number, 20,000 newtons. For our freedom friends, this is 4,500 pounds.
Okay.
Which is, I don't know, 4,500 pounds I know is enormous, but I don't have a good feel for that. Like, what is that? So I did a Google AI search.
Okay.
So the maximum force a human can generate with a punch is estimated to be around 5,000 newtons, roughly equivalent to the force exerted by a half-ton weight on Earth's surface. Okay, I guess. Elite boxers and fighters can often reach this force, while an average person is 750 newtons. Kind of. I guess that's right. A normal person can punch significantly weaker than a elite boxer.
Right.
And so I guess the question is, if this is elite boxer at 5,000 newtons and K2SO4 is 20,000 newtons, that's a factor of 4? 4 is it?
4, yeah. So 4 times 5 is 20,000.
Or for compared to a regular person, 6? 7? 40.
Yeah.
20,000 divided by 756?
You're saying 20,000 divided by 750 newtons. Let's round that just to 1,000, about 20 times a normal person.
Yeah.
To me, these numbers seem really, really reasonable because K2SO is a robot.
26.
He's metal and actuators, whereas humans are soft and fleshy.
Yeah.
So we can't generate that much force, and he just does a casual backhand, and he can generate 4 times top level athlete. That makes
top level
a lot of sense
or
to me.
26 times like a regular person. I think that's entirely reasonable.
I think that's
and
entirely
it's also reasonable with how hard the guy like flew. Like if you punch a guy, like, he's not gonna fly like that. But with the strength of 26 normal people. Or 4 like elite boxers simultaneously punching.
Yeah,
it's gonna hurt.
Boom.
Makes
sense to me. Yep.
Also, check out that 0.41 seconds. That 0.41 seconds is the time from the impact to when you hit the wall. That's actually erroneous. Might be. So why do we not use that 0.41 seconds? Because once the contact has been interrupted, the acceleration is no longer happening. This at the point where the guy's in the air, he's just coasting. We don't need to count that time. We only need to count the time that's 0.04 seconds. That's the single frame. That's when he's still in contact.
I guess we could use that 0.41 seconds to calculate the velocity from post-contact to wall contact if we wanted to, which we did not do.
Oh, yeah, sure. Yeah. That's another way to do it.
Yeah. The critical... It's how much time determining the acceleration is by how much time his arm is actually in contact with the trooper.
Yep. Because that's the acceleration phase.
Right.
Cool. Super cool. That K2SO's forces are very reasonable, very accurate.
Very reasonable given the dynamics we saw. Yeah. Very, very cool.
Indeed.